Right. How about now?
Ooh, hello. Okay, great. Can people on, looks like my mic's bouncing now. This is very, very loud. Is this extremely loud for people on Zoom or is it okay?
It's okay.
Hi, can somebody on Zoom please say something? JDip, are you able to hear us?
Yes, I can.
Now maybe we can't hear them.
Right. But we have computers coming back, so that's just again only one choice.
Or maybe they can't hear you. Okay.
So that's one problem.
Right, but we can't hear anybody else yet. So
Oops, one sec, whatever.
so audio source PC, that's right. It's not muted. Oh, video volume 0%. That doesn't sound right.
Okay, could somebody on Zoom try to speak with us again?
Hi, mute. This is Jadip. Hello, is it audible now?
JDip, can you hear us?
Yes, I can hear.
Oh, great, we can hear you now.
Okay. Too many seconds.
All right. Well, just in time. All right, I see it's let's see. JDip, do you want to go ahead and set up your screen sharing while a few people are trickling in, and then I'll do an introduction and you can go ahead and get started?
Sure. Is it visible?
Yes, I can see your screen now. Can you go ahead and make it full screen? Thank you. Okay. Does this look good for everybody in this room? Okay. All right, great. Well, thank you guys for joining us for the start of the Physics Fall Seminar Series. We've got a full schedule. For people that are in the room, they can check out the schedule up here in the front when they're on their way out to see what's coming up next. For our first talk this semester, we have a presentation from JDip Singh. So JDip is a student that's working on NOVA and DUNE. He got his master's degree from the Indian Institute of Technology in Bombay and is currently finishing up his PhD at Lucknow University. And he's going to tell us today about work that he's been performing to reconstruct high energy muons with the DUNE FAR detector. So with that, JDip, I'm going to go ahead and let you take it away. And for people in this room, if you have questions, you're going to have to filter them through me because I think they need to go through this microphone to make it out to Zoom. So pass it to me and I'll tell the speaker to pause if we have a question in the room. Okay, JDip, I'm going to go ahead and mute for now and let you go ahead and take it away.
Thanks, Matt, for the brief for the introductions. So hello everyone. Good afternoon. So I will present an energy reconstruction technique for the very energy muons with the DUNE FAR detector. And this work is done with the DUNE collaboration FD group. And this is also with the Tom So this is a very brief discussion. So I assume the audience will be a little bit will be familiar with the DUNE technologies. So this is the outline of my talk. First, I will discuss the goal of this work, and then the muon energy measurement techniques that are commonly used for the muon spectroscopy, and then the simulation and reconstruction stuff, and then the future work. So this is the goal. So our goal is to reconstruct the very high energy muons that are originating from the cosmogenic neutrinos as well as from the cosmic rays. And one can also look for weakly interacting massive particles using neutrino-induced upward slowing muon. So this is already being done for the super-Kamikonde collaboration. So one can also do the same thing for the DUNE detector. And this kind of astronomy works at the TV scale. And the methods that we are using is already being tested for the ice cube and super-Kamikonde detector. So DUNE FT may also use this technique for the detection of very energy. This is very basic of the muon spectroscopy. So for the MeV to GeV range, we use the muon range methods. And for the energy range of tens of MeV to GeV range, we use Coulomb scattering methods. And this is used for the Gauss and micromuon experiment. And the third one is magnetic spectroscopy. This is used, this is basically based on the strength of the magnetic field. And it is used for the GeV range of muon. So experiment like MINOS and CMS are using this technique. And DUNE is not a DUNE 4 detector is not a magnetized detector, so one cannot use this technique for the DUNE. But I have worked for the INO collaboration, so INO is a magnetized detector, so I have used that technique for the INO collaborations. In this work, we will be using the energy deposit dependent methods, and this methods works for the energy range of hundreds of GeV to TeV range, and experiment like super-Kamikonde and ice cube are using this technique. Again, this is a very basics of the muon stopping power. As we know, this is the for very high energy muons. So basically, one can write the stopping power as a linear combination of ionization as well as with the radiative process. For the case of very energies, the dominating process is the radiative one, and the radiative process includes Brahms long pair productions and nuclear interactions. So one can see here this blue vertical line. So this is the minimum ionizing power for the, this is the critical energy for the liquid argon, and it is around 484 GeV. So above this, the leading processes are pair production, Brahms long and nuclear interactions. So our goal is to get the fraction of energy deposition through these processes and collect and correlate this fraction of energy deposition to the muon energy. So at this energy, there will be tracks as well as the associated showers. So we will be getting the fraction of energy deposition through the tracks as well as through the showers. So this is the one source that is observed at the ice cube neutrino observatory. So once this phenomena happens, so there will be neutrino as well as the gamma rays. So these two species can be observed simultaneously on the telescopes. So this is observed on the 22nd September in 2017. So this was the first detection from the ice cube collaborations. Later on, there are several other lasers are detected at the ice cube detector. This is the layout for the DUNE 4 detector single phase. This is for the single phase. So in this phase, the detector will be fully submerged into the liquid argon. So once the charged particle will pass through the liquid argon, it will ionize the argon atoms, and the ionization will be drifted toward the anode planes through the electric field. So this ionized electrons will be collected on the anode planes, and these signals will be observed as a heats. And in this work, I will be using the heats and the space points. So this heats from the other information, I will reconstruct the space point. I will come to the later. So this is the events are at different APs. This is 10 keV Muon event. So one can see there are tracks as well as there are souring. So that may be at the initial stage of the tracks, or in the final stage of the tracks, or it may be throughout the tracks. So there will be, as I already said, there will be tracks as well as the several sours. So our job is to get the complete energy deposition through the tracks as well as through the sours. I will just change the slides. So for simulation and reconstruction, this is the setup. This is the event generation setup. I mean, for the event generation, we are using the particle gun event generator that is available in the GN4, and muons are generated and propagated horizontally along the lengthwise of the detectors. And while hitting the muons, angle are also varied, and coordinates are also varied for the X and Y plane, in the X and Y planes. We have, this work is limited for the monogenetic energy. So we are generating 10,000 events for the energy range of 100 sub GeV to 50 TeV. So there will be hits and the space point reconstruction. Okay, before I will come to the reconstruction stuff, I will just give a small introduction about the parameters that we have used for the correlation. So this work is already done by Kevin. So he just used the simulation channel data container, and that energy deposition is based on the GN4 model. So he didn't work with the reconstruction stuff like heat and space point. So my job was to do the same work for the reconstruction object like heat and space points. So he performed the analysis for the top 4 parameters. So first one is average energy depositions and the RMS energy deposition, and then the energy deposition and RMS for the sour only energy measurements. I mean, excluding the minimum ionizing power. This is third and fourth parameters only from the sour energy measurements. And then I also performed the analysis for 2 objects that are made from the reconstruction step, heats and space points. So heats are used to get the total charge, and from the heat integral object, and for reconstruction the space points we are using Pandora. So this is the first 4 histogram for the 4 parameters. This is for the 10 TeV event. So one can generate similar histogram for the various energy, like starting from 100 GeV to 50 TeV. And for our work, we generated from 100 GeV to 50 TeV. And these histograms particularly for the 10 TeV events. And this is 2 parameter reconstructed from the reconstruction object. And the left one is from the for the full track length, and the right panel is for the small track length. I mean, so full track length means the complete track track segments containing inside the detector wall. And the start track length means we are taking only 5 meters of track length. Again, this is only for the 10 TeV muon events. In the same way, we generated events for the various energy for making the correlation. Okay, now I will just give a little bit information about the track length estimations. As I shared, I use space point for the reconstructing the track length. For the space point reconstruction, we are using Pandora algorithm, which is already available in the LAR software. So this is this black circle are the reconstruction space points for the this is for the, I think this is for the 10 TeV event. So one can see the reconstruction space points are not collinear. So we use PCA algorithm to get the average position and the direction of the line. I mean, we are using geometry to get the intersection points of the line and plane. So this intersection of line and plane will give a track segments, and that segment, so one can get the track length from this algorithm. So once we have the track length, so we can get the total charge from the heats, and then we can get the dq by dl. This is the true track and reconstructed track length from our algorithm. Again, this is for the 10 TeV and this is for 1 TeV and 10 TeV events. And we also tested this algorithm for the cosmic ray sample. So that is already available for the DUNE collaboration. So we separated the stopping muon sample using this algorithm. So that stopping muon sample were used for the calibration. I am not discussing here. Maybe I can provide some information, or some of my previous talks have discussed this stopping muon analysis.
Okay.
And David also.
Hey, JDip, we have a question in the room. So I think the
Okay,
question
sure.
is why are we seeing that the reconstruction, when it gets the when it gets the value wrong, is biased to high reconstructed values? Why is it overestimating the energy in the reconstruction?
So this length, right?
Yeah, why do we have the fuzz only above the diagonal line?
Okay. Sorry.
Or if you're going to tell us that in the later slides, we can wait too.
No, let me just discuss it. So this is due to the PCA algorithm limitations. I mean, we are calculating the average points. So if some space points are too much away, so we are getting uncertainty in the direction reconstructions. So due to that overestimated or wrong, I mean, due to uncertainty in the direction reconstruction, we are getting a little bit, overestimated track length.
So, so you're basically saying that whatever it does to, to find these space points to pick up the track has a tendency to sometimes pick up things that are not part of the real track and include them. Is that what I'm understanding?
No, they are sour. So these are very energetic events. So they are sour. So space point will be too much away from the track. I mean, from the track. So there will be track and the sours. Due to sour, the space points will be too much away from the line.
Okay.
So that gives a wrong directional directions. Little bit. Maybe I will show some pictures. Then it will make more clear.
Okay.
Later on.
Okay, so it's about it's about the direction, that if
yes,
the direction wrong, somehow it relates that back to a higher energy.
Okay. Yeah. So for getting the equation of line, we are using average position and equation. Direction of line. So If we get the wrong direction of line, then we will get a little bit bigger track length.
Okay. We can come back to this. Maybe it'll get clearer as you go through the rest of your slides. I did
Yeah,
have
sure,
one more
sure.
question while you're on this slide. So your Pandora instance that you're using here to find the space point, is this a generic version of Pandora that's been trained on all events, or has this been trained to find space points for these particular kind of events that you're working with, or is this just like the out of the box Pandora that people are using?
No, this is the main version that is used by whole DUNE collaboration. I mean, whole DUNE collaboration is using this version of Pandora.
Yeah, I was just curious if maybe at the end or later.
No,
we
no,
can
no.
discuss
I
if,
used to get updated with this alias soft.
yeah, would there be any benefit to making a special
Yeah, yeah.
Pandora that's trained on a large sample of high energy muons that might improve the reconstruction? So, okay.
Okay.
Okay. All right, go ahead, you can continue.
Okay, so in the previous slide, I shows the list of parameter histogram. So now our job is to correlate these observables with the true muon momentum. So for ordering this, we are using Feldman-Cousins ordering. So this ordering basically takes the 68.3% of the events for that energy, and this will make a belt, I mean, a confidence interval, and this confidence interval will be used to get the confidence belt. Basically, we are using Neumann construction for correlation. So we will getting the confidence interval, then confidence interval will be used to get the confidence belt. So the same thing for the dq by dl for the 1 TeV and 10 TeV events. I mean, for the short track and for the long track events. So this is the Neumann construction build made from the confidence intervals for the various energy. So this is for the 4 parameters again, and this is other 2 parameters. Once we have this confidence belt, then one can draw a vertical line, something like this, and then the intersections of this intersection with line and belts will give a upper limit and the lower limits on the vertical scale. So vertical scale is just true muon momentum. So once we have this interval region, then one can get the true muon momentum by taking the average of, taking the average and the exponent. So this way we can correlate with the fraction of energy deposition to the true muon momentum. Again, this is for the average energy on the wire. I mean, for one parameters, same way we can do for other parameters. Once we have that, then we can check the resolution. So this is the Muon resolution for the 10 TeV energy events for the 4 variables. And this is for a reconstructed object, a resolution for the 10 TeV muon events. Same way one can get the resolution for the other energetic events. And this is the final resolution for the all energetic events, muon events. And
could you go back a slide? I'm just curious, why are your statistics so low on this? Is it hard to generate these events?
So the length, when we estimated the length, so there are some limitation we are putting to remove those events. I mean, we are not considering the isochronous tracks and some other tracks. So we are excluding there are some events. So
are you using some sort of, I mean, did you generate this sample? Is this a special sample that was generated for these studies, or is this some I mean, did you basically filter some common
No, I generated these events. So
generated them? Yeah.
for calibration, I am using already generated events, cosmic ray samples. So, but for this study, I have generated my own events.
And this is a special high energy muon.
Yes, and this is 10 TeV events. And this is the complete.
Sorry, JDIP, we have another question in the audience here. So the question is
sure.
on the left of slide 15. Go back one more.
This one.
Yeah.
Yeah, it looks very low statistics, but the numbers are in the hundreds. So somehow it doesn't agree.
Which number is in the hundreds, Holger?
That's on the scale.
Oh, yeah. Yeah, I see. Oh, yeah. So the question is, oh, right. That's interesting. So the question is, it looks like you have thousands of events in here, but they're all getting binned into like the same kind of, like they're all, the question is basically, it looks like it's low statistics, but when we look at the number of counts actually on the y-axis, it seems like there is a decent sized population. Why are they all falling into these kind of discrete locations or specific locations in these histograms? Like, why are there the gaps that we're seeing like at, you know, just to the left of 0? I don't know if you know the answer, but it just seems a little bit unclear why if you have several hundred events, the two bins that are kind of to the left of 0 are like so different in scale.
So our code do some interpolation, extrapolation, and if there are some criteria to select the events, I mean, so I think due to that criteria, we are removing some events. So
is the number of events that's on this plot, is that scaled in some way to match some exposure, or is that the real number of events you have?
this is the real number, but there are some events that are not properly reconstructed. We are removing those events. So of course there are some missing events here.
Okay. All right. Thanks. Why don't we keep going?
So this is the resolution for the complete set of energy and the whole list of parameters. So still there are some issues for higher energy region. So we are looking the issue and we are doing the systematic analysis. And we are trying to means I have submitted an LOI to do the same analysis with the deep learning algorithm, and it is I have submitted in a Snow Globes conference. So as this technique is using deep learning, it is done by the STU collaboration. So we are also planning to do using the deep learning methods, and MIT group have already done little bit work using the deep learning algorithm, and we are working with that with the MIT group. We are also doing systematic uncertainty evaluations like muon radiation modeling, electron saturations, recombination models, and in the dense shower and electron lifetime. That's all I have. But I want to show one thing that I didn't answer earlier. Is it visible now? So see, sometime we, due to heavy showering or some saturation in the detector medium, or might be due to electronic noise. So these space points are too much away from the red line. This is the reconstructed line, but The green one is the trajectory length, I mean, true track length. So due to this distortion, we are getting some issue with the direction reconstruction. So due to that, we have overestimated the track length, as I said earlier. And this is the isochronous, right side is the isochronous events, but we are not taking these isochronous events in our analysis.
I see. And then once you
And
have
there
this,
are some stopping muon events. I mean, so maybe this one. So these are the stopping muon events.
okay.
So you will see something like this. So these are the stopping muons. So this will be used for the calibration purpose.
Okay. So this goes back to the question I think Dr.
Yeah.
Salier had earlier.
Yes.
Uh,
Yes.
So let me just make sure I understand the basic idea of how this works is you find the space points with Pandora, and then you have this this set of variables that you look at to try to determine the range of the whatever the muon might be that's coming in, and then you use this average DEDX to determine the energy of the muon in the detector. And since you think it's longer than it actually is, you will overestimate the energy that you're assigning to that muon. Is that right?
Yes.
Okay. So what is the proposed remedy for some of these features? Is there something you can do to improve that?
So we are trying with deep learning algorithm. I mean, I have submitted that, and we are also improving our algorithm. We are also estimating the systematic uncertainties and all this system.
Yeah, I would guess training Pandora on these particular types of events probably would help it understand this.
Yes.
Okay. Great. So JDIP, we have some time, so we can open up for questions right now.
Sure.
I've got a few. So can you go back to the slide where you show us the 6 variables that you use to use for your algorithm? Yeah, this slide. So I was a little confused because the first 4 here, 1 through 4, the true energy deposition measurements, this is truth information that you're getting out of Jayon, right?
Yes. Sync channel. I mean, there is a data container sync channel called sync channel. So that contains basically energy deposition model in the GN4.
So I guess my question is how can you use that? I'm imagining then we have DUNE running and we want to measure high energy muons that are actually coming into the detector. How do we use those variables if they're truth variables?
So we will be using dq by dual, and so from the dq by dual, we can get d by dx. I mean, using the we can do calibration. We can correlate d by dx to the dq by dual. So this way we will get the average energy depositions.
So tell me then again, what are you doing with these true energy deposition variables here? What are these useful?
So this will just this is just to get an idea. I mean, whether it will be possible to work with the DUNE detector or not. So this will give a rough idea to us. I mean, this much energy are deposited into the detector, and if one can reconstruct, then we will be getting some kind of confidence that one can use those energy deposition to do the reconstruction.
I see. So the idea would be, you would hope that these can turn into measured right now you're just using the truth as a stand-in, and the hope would be you would have some
Yes.
calibrated, measured versions of these things once the DUNE
Mhm. Yeah.
better understood. Okay. All right. I think I understand now. I can ask the audience here, and also those on Zoom. I can also bring the chat. If you want to unmute and ask a question on Zoom, or type in a question, I've got the chat open here. I can convey those to JDIP. Are there any other questions in the room here?
So this is a very brief talk. I can provide some more detailed discussion later on if needed.
Sure. I have one other quick question just so I can understand this. So the small track length sample, what does that mean? Like, what is that's a fraction of the full track. How do
Yes,
you
yes,
decide,
yes.
how do you decide what part of the track you're looking at for that?
So once we have the full track length, so we put the sphere, I mean, on the end point of the track, and we started rotating that sphere. Let's say if the diameter of the sphere is 5 meters, so we are rotating that sphere along the line, and if the hits are contained within that sphere, so a sphere of diameter 5 meters, so that will give us a dq by dl.
Okay, so this is essentially the last 5 meters of the track.
Yes.
Okay, great, thank you. All right. Yeah.
Known mechanism why gamma ray burst is.
So JDIP, we have a question from our astrophysicist in the room. He wants to know, this is from Dr. Ferguson. He wants to know, what's the mechanism for neutrinos to be created in coincidence with gamma ray bursts? Is there a known mechanism, or is it just? So like he's thinking about back very beginning in your introduction where you're talking about where the high energy neutrinos might come from.
So those neutrino may comes from the blazar as well as from the other astrophysical sources.
I think he was asking, do you know any more details about how they are produced from the blazar? How those neutrinos?
So these are basically protons. When proton interacts with the secondary nucleons, so this will produce pions as well as this will that will generate pions. So that pion will further decays. If this is neutral pion, this will decays into 2 photons, and if they are charged pions, they will further decays into muons and neutrinos. So this way we will get neutrinos and photon. I think this is what he asked.
Great, thank you very much.
This is something like we accelerate protons and we hit the target, something like similar way, in the same way.
Okay. All right. Great. Are there, let me check Zoom real quick. Let me check the chat. I don't see any questions on chat. Any more questions in the audience? Okay, if not, I know it's very late for JDIP. It's about 2 in the morning where he is at the moment. So why don't we go ahead and thank him? So thank you very much, JDIP.
Thank you, thank you.
Have a good evening, and we'll be in contact with you. Okay. All right.
Sure,
Bye.
sure.
All right. Thanks so much.
Okay.
Okay. Bye-bye.
Thank you. Okay, bye.
Okay. Bye-bye. All right, guys, everyone else on Zoom, we are going to go ahead and leave the meeting. So we'll talk to you later.